Um, Now it's final day. After 4 long days, there will be a final day, closing everything. So we have now learned the basic theory, really basic theory on single crystal X-ray diffraction, what happens with all these things. Have already had an exam. We've been absolutely fine. Some questions there related to work, what have been doing here. Now, yesterday we went through the idea how it really happens in real life program. We were able to solve the structure, and we were able to see that, okay, everything is fine. So now we move to the final step, analysis of the verification of the X-ray structure. This is very important. This is at least important thing than growing the crystal, really having able to analyze what you have done. In many cases, this can be misleading. That sometimes the X-rays are not telling you the real story. There might be an incorrect atom somewhere that, as you yesterday noticed, that the program was giving you something and it might not be correct. So you have to yourself see that it's chemically reasonable. These things happen sometimes that the X-ray diffraction doesn't know the atom types, can give chemically incorrect answers, or then the computer program, like yesterday, you noticed that it was calculate. I asked it to calculate hydrogen atoms, and in normal cases works perfectly. But sometimes this happens and miscalculates something. So it's up to us to check that that is correct. So the final this type of lecture is this 9, and then the 10 I will go and show you which kind of supramolecular structures we have been doing in the past 40, 30 years. This is more a little bit, then 10 will be more like a scientific discussion and a scientific talk, but not focusing on one topic like I did yesterday afternoon, but giving snapshots, different kind of things, what has been, can be done. X-ray. Some of them are really old ones. But let's go now in this analysis part. So what do we do after we have done the X-ray structure? So now the finalized X-ray structure, we are happy with this. It is there. Everything has gone green. You here, yeah, all the atoms are correct, and now we know that these here are the background. We don't have to worry about them, so everything's fine. And now we have to do what we normally do. We do tables out of it. Call it crystallography tables. And now within this frame, there is a very simple and easy procedure to do this, because there is now a report. When you tick the report, it will open up a submenu here, and each of the individual abstract structures you look into. So you can see here is collection, crystal, diffraction, absorption, publication, blah, blah. There's a lot of info here. But because it's a new structure, some of this is, of course, blank. We don't know it. But the point in there is that we want to have a full report out of it, and which will be in an HTML format. So we can open that at the browser. That is something what we do. And it's very simple. When you have done it, this report menu, which is now activated, as you can see, yellow, click this make report. So this make report automatically reads everything what you have done. It reads a ZIP file, and it also extracts some other information which might be there. So it's a very nice tool. And now you can see we are now in the folder demo where we have all our files. Remember, we started from 2 files, and now it's about 10. And one of them, now the table file in HTML format, and now because we started with our structure name was demo, and now you can see that it gets demo tables. That contains all. You can easily open it with web browser, and it looks like this. So it really, this is a most important table. That sense is crystal data and structure refinement for demo. For example, in previous years, this was always a part of a publication. So it was always published, it was part of the publication. But it disappeared some 10, 15 years ago when ZIP file, you will, what is a ZIP file? That's the crystallographic information file with the program rights. When this came available, then it said, okay, you can find this information either from the SI or from the database. Typically, this information now given in SI, depending on, sometimes you might report these inside the paper, but typically it's not needed. So the most important, the crystal refinement data. In here, what it tells us: name, the chemical composition, molecular weight, temperature, where it's done. Now, crystal system, orthorhombic space group, very important. Then the unit cell ABC. Now all the angles are 90. Calculated volume, how many molecules these we have in that unit cell, 4. And then from these information and of coordinates, calculates density. So this is now the first time the density, so it's there. And this is, remember, the idea, it's mass over volume. Can then calculate this density when we know all the atoms, atom types. And now this mu here, this is absorption coefficient, which tells us how strongly atoms in structure absorb X-ray. And this is not very important number, but in certain cases, if this number is big, let's say it's 50, 100 or more, then it's normally indication that you should change the radiation. So it absorbs so much that given wavelength, like in this case is copper, then it's okay. Sometimes referee might say, okay, you have to do that with molybdenum. But that's not so critical anymore, and the reason for this is make absorption correction also with the new instruments for the copper radiation. So that is not so crucial. Previously it was valuable. Then this F000, actually the number of electrons, and that number of course indicates how many electrons, and it is an indication about also diffraction power, but also about the content. This number is actually 4 times the electrons of, we have 4 molecules, but it prints it out. This was again an important number which is indicated 20 years, has lost now its importance. It's not so important. So what are important is the unit cell, of course, and then base group, and then the molecule itself. And then crystal size, we didn't indicate the crystal size, but this is crucial information. So when you are putting a report up or so on, always have to measure the crystal. And in this case, it was not measured. We didn't have the information anywhere, so it gives question mark. But the nice point in here is that you can edit. So you can go there and then you have your notes, and the notes say that, okay, the crystal is 0.1 times 0 times 0.3, and then you type it there. And now you can see, which is also an important information about the radiation, molybdenum. This is information from the data collection, that what is the range of the reflections we have been collected. That's there. And now this gives now the index ranges to H, K, L. You can see H, K, and L. So it means that it has collected all information from minus 8, minus 12, minus 24, up to 9, 12, 25. And now if you look, there is a nice rule of thumb here. If you look for, because H relates to the A-axis. And the A-axis is 7, but now here the 8 is bigger. It's minus 8 to 9. So it means that our resolution then more than the length of it's more than 1. And then if we look for the B, so it's 10, here we go 12 to 12. And then in here, it's 20. So here's 24, 25. So you can see always we aim that these HKL ranges are bigger than their Schnitzler axis. So it means that then we have a higher resolution. If they would be the same, then it would be that it would be 1 ohm separation. In some cases, it would. But typically we aim for it. This is how many reflections it has collected. And this is quite a lot. Remember when we saw a few of them, but it's 7,695. Now, they have been measured several times today. Same thing. Remember there is 002 and 002. There's 2 times. So when you take an average and look for independent reflections, it's about 1/2. So that is a real number of reflections we are using. So it's more than 3,000 slices of the structure we have to have in order to get the structure. And we have to collect all of them, because if we don't, then the checking program, what you will later on, will complain. They say, now there is something wrong. And then the referees or anybody who is reading this, an expert, says, now there is a mistake in the data collection with the diffractometer. And now that's the idea. And then it gives you how many data you have. That's the number of those reflections. Restraints, we can have inside the program induce some restraints so that some parameter doesn't move. But in this case, there is 0. And then this is the parameters. So the idea is that we have 9 parameters for each atom, each non-hydrogen atom. And this indicates that, okay, we have a reasonable amount. It's not a very big structure, only 210 parameters. Point to look for the mathematical calculations, what it's doing. It is using all these 210 parameters, each of these reflections. So it's a huge calculation. It's really, I remember a time when we had slow computers, not even. So this kind of a calculation, what I was showing you yesterday, second or so, took hours. Because it's a computer which is doing this calculations. The amount of calculation. Okay, that's the idea. The goodness of fit is just a fitting value, which should be 1 if everything is fine, around 1. This is grossly out from 1. Then it's a normal indication that there is something wrong. And then the R values, remember, these are the values which tell us how well our model fits with the data, and this number should be as small as possible. There are 2 values. One which we cut the weak reflections out, so they only accepts reflections which are higher than 2 sigma, the normal, and then we can have all of them. You can see that this number is always more. But this number, there is no absolute value. Value can be 2 or this kind of a thing, 0.02, or it can be 0.1, so 10%. They are both good, because that is not the idea. The R value itself is not proof for that the structure is good. And then this is also important point. You have a largest difference. Oh, it means what is there when all the atoms are taken out. So that's the background. The background is, so it's 0.14. Remember yesterday I told that hydrogen, if it would be there, would give 1. So we know that it can't be any. And now, then there is an important point. Yesterday, remember we discussed about the started to think that we have a racemic crystal. We know the racemic compound. We know that it's optically pure. And the optical purity means that it has 2 options. If crystallizes in a space group which is centrosymmetric, meaning that there is a mirror image of it, it's the same as left and right hand. So there has to be 50-50 left hand, 50-50 right hand, and it's absolutely okay. It's very common, actually. And that's racemate, that's racemic. But if you dissolve this and put it in the enamel tube, you don't see the differences, because in NMR, the enantiomers are the same. You can't see the difference. But in the X-ray diffraction, if they are, if it's a pure enantiomer, then there's a difference. And now this space group here, this 1, 2, and 1, so-called chiral space group, and there is no mirror image. And when this is the case, the program automatically makes a calculation. What does this mean actually in real life? I don't have a board here, but normally I do it in the blackboard. If you consider HKL, the 002, for example, and then you look for its the other half, it's 0 or a -2. So in a case when there is mirror image, they are the same. The numbers are the same. But then if it's not the case that there is not a mirror, also there is no mirror between these two numbers. So the 002 has a different number compared to 0 -2. And now this difference depends on many things, but in this essence, it depends on the handedness of the molecule, what you have. And then we can use this separation to do a mathematical calculation. Is it the left-handed one or the right-handed one, the molecule? And then this is used by comparing these, we call it Friedel pairs. So the normal 0, 0, -2 are Friedel pairs, should be equal, but in this case they are not. Use this difference to look at the left-handed or right-handed. And there is a parameter here, the lower part, called a Flack parameter, and this comes from the why it's called the Flack parameter, because it was an UK crystallographer called Howard Flack who actually designed this parameter. So it's a mathematical formula or process to calculate the differences from the data, from these not equal pairs. And this number here, it's been tuned so that it's 0 when you have the correct enantiomer and 1 when it's incorrect. So what it means that if you do this calculation and you're finally there, and then you get the Flack parameter of 1, it means that you have the wrong enantiomer. What you have to do, you have to tell the computer program to reverse all the coordinates. It can be done. You don't have to change the crystal because it's that. Only the coordinate set has incorrect handedness. Just reverse it, and then you have it, and then the number becomes 0. So that's the idea. If you are ever looking for structures of chiral molecules in the literature, so always look for this Flack parameter that is 0, but that's not enough, because in addition, the number here in the brackets, which is standard deviation of this value, very important, because if this standard deviation is big, then statistically you cannot trust the number. That would be the case that even if it's 0, but the ESD high, then the referee might say that, okay, I don't believe because it's so uncertain. In this case, we are very lucky because there was chlorine and fluorine atoms, where this separation of this 002 and 00 -2 big. And the more heavier atoms we have, the more bigger are the differences. So it's very complicated. This calculation is very complicated if we have a hydrocarbon. But it can be done. A very specific technique can be done so that we also have the handedness of a hydrocarbon. But as I said, the X-ray diffraction based on the Flack parameter, based on the difference between data, the only experimental tool method where you can for sure say, okay, my molecule is left-handed, right-handed. Consider pharmaceuticals, for instance. Very important to know what enantiomer. That's the case. And the Flack parameter is a correct absolute. It's call it the correct absolute structure or configuration parameter. And now when we have a non-central symmetric space group, which means that there is no mirror image, the correct value should be close to 0 with the small e's. And in here, it's 0.01 in brackets 2, it's a very good value. We know that within 99.5% certainty is 0. So then we trust that that's the case. That's the most important table because it contains all the information. And if you have chiral molecule, non-centrosome space group, we will get the flak parameter. But if it's not, then it doesn't appear because you can't calculate the flak parameter on a case when there is a mirror image. It's not calculated, so you don't have to worry about it. But then what it prints out, of course, and previously, let's say 25 years ago, this was also printed in publication. The real publication, not even an SI. At that time, there was no SI, so everything was printed in the manuscript. But this is the fractional coordinate and the thermal parameters. So chlorine, fluorine, so on. You can list. They are not in order, but they can be ordered. But that's the idea, is that if you would have to write a report, normally it's not included. It is in the file. And then also it makes a more accurate table on the anisotropic this parameter. Remember that the atom when we started was like a ball, but when we finalized, it looks like an ellipse. So the anisotropic displacement or thermal parameters, such as numbers, have to worry. But this is not at all important. Printed, but you actually don't need it. But then there are two tables which are of importance. It comes automatically there. So these are the bond distances. So now we can see here that carbon and that carbon, it's chlorine, sorry, is 1.72742, and the standard deviation is 3. Now, when you consider the accuracy, the length scale is 10 to the power of minus 10 meters. Now we have an error in the third digit. Extremely accurate. So it's difficult to actually understand this because we are always on an Ohmström scale, and then we are roughly on 1 something. But Ohmström is 10 to the power of minus 10 meters. Then we have the error in here. You can easily see that it's extremely accurate. And now the idea is that by historical reasons, I don't know why, maybe that was the idea when there were not very accurate measurement devices. This PSD indicated so-called 1 sigma level. The 1 sigma level is 66%. And it's quite uncertain. So what you have to do, if you want to study statistically bond distance, you have to multiply this number by 3. Then you get the 3 sigma level, which is 99 point. And this you can do sometimes if you are doing an analysis. Is there statistical differences between the bond distances or angles? Then you have to take this into account. But in the normal life, don't worry, because it's always reported like this. And it's a historical reason. So the 3 sigma would be better nowadays, because it's more accurate. Of course, it's easy to calculate. But that's the idea. And here you can see then fluorine carbon distance about 1.35 roughly. Then there is O carbon, this is 1.4, this is an OH distance. Then we have here again one of the same fluorine carbon 1.3. And you can see, even though it's the same bond, carbon fluorine bond, it's never exactly the same. So you have been told probably in the course that benzene ring, the carbon-carbon distance is 1.39, the angle is 120. But this is ideal, it's idealistic value. The real values always have errors in, never the same. Like in here, some of the distances should be the same. Like here we have, this is from the benzene. You can see there are values are really different. But within this experimental error, they are the same. So the absolute value is not the same, but within the experimental error. So this is what we can extract. We will extract a lot of information, but we have to also critically look into information. So that is printed. Here we can see nitro group is clearly, so O nitrogen O distance clearly shorter than the carbon-carbon, carbon-nitrogen bond. Now in here we have another table which is actually coming from the coordinate. This is the angle. You can see there are more of the angles than this. Of course, because we can have many of the same, but we can have an angle in this direction or that direction. And the same applies here. Look. But now the angle accuracy is much smaller. You can see it's now in a tenth of a degree. So the distance is much more accurate always than the angle. And the same applies here. This is 1 sigma. In real life, you should multiply that 3 if you want to see still different. But anyway, in most of the cases, the angles are less accurate than the bond distance. And then either a report kind of a thing, like my course is going, they have to add these things that show that, okay, yes, I have these. And then it really adds additional things. It calculates the hydrogen atom coordinates. But this is really interesting because they were calculated. They are not determined. So we let the program to calculate. This is also an old standard way of showing also the hydrogen atom coordinates. But of course, this is not needed. You don't need to know the position of hydrogen. Calculate. Then it makes a short, this program makes a short additional summary. You can actually use different versions of you can see here, this is now the crystal data in this form. So it writes the same information in the chapter wise, but the other was a table. So it's up to the person always think about, okay, shall I make a table or shall I write them in a chapter? And that's the idea. So this is what the program prints as a report. We can look in. But where is it based? So the actual idea, where is the information what we have gathered? That is actually in there. When we did the final part of the refinement, we clicked this ACTA there. The ACTA command didn't use that the program write a ZIP, so-called ZIP file. So this is ZIP file. It comes from the, so it's name.zip. So this is the ending for this. Where does it come from? It comes crystallographic information file. And it has a different format, has a certain format file. So it had been agreed, I think 25 years ago, has been agreed how to do this. And the idea, that's an ASCII file. It's a normal editor. You don't need the Word or anything for this. You can use just a typical ASCII WordBat or something like that, and you can go and edit the file. But there is, if you go to the Chemstructural Database program site, you can find an NCIFR program, which is free, download it, and it's nothing more than an editor. So this is an opening for NCIFR, and it uses this coloring code for this. So the blue ones are the format of the information in what we call the CIF language. So you can see it says, okay, when this is audit creation data. So this means that, okay, when was the report was done in 2018 or the CIF file. And then you can see there are last publication contact author address. So they could be my address, so on. In here, it automatically, it says publication section references. It automatically knows the program which has. And now, chemical name systematic, chemical formula moiety, chemical formula sum. So it's automatically inserted. Then chemical formula weight. As you can see, has a certain format of indicating this. If there is no information, then appears as a question mark. But if you have this information, you go and edit. You can type it there. Like there, I could create this publication contact author name. I could write here between these brackets, Karilis. Then I would be like the. And this is how it goes. And then it comes here, it comes coordinates and all the other information. So what to do then? Because this is the thing what we have. We have finalized everything. And now we want to have the final. We have done the check by ourselves. We have seen there some coordinates and we have seen there are on distances, angles, all these kind of things. I will then show, it's also shown here in a cartoon, but I will also show you we can program, analyze our structure visually. But this is the printed version, but also. So the point in there, here you can see that's this is Chemistry database website, and you can see here that you can have our NC for Linux, Mac, go there. But the point is there that then when we have everything done, we are happy with this. We have to do one final check, and this is must nowadays, that no structure will be accepted anywhere if this is not done. That should be the case. And this is so-called GIANxEF. So the CIF file is the file what we made, our file. This GIANxEF is a program which is not sitting on your computer. It's a server of ICUR, International Unit Crystallography. So what you do, you submit your own CIF file, this place to do the check. So that is like an independent person, independent entity has checked your data. Not okay that you say my data is okay. The idea is that this system makes it and it writes a really important. So the idea now, GIANxEF reports on the consistency and integrity of crystal structure determinations reported in the CIF format. It checks that its formal is correct, but if it's the total cheat, cannot see this because it doesn't know what is the real structure. But it can see if there is something missing, if some parameters are not correct. If the person, for example, has edited the file and added their incorrect information, either on purpose or without the purpose, this check will tell this. And that's the idea. And it prints out the report. So the idea, select your CIF file. So we will browse here and we will go and put it in. And then we can here control what it outputs. So it can output an HTML file so we can see it, or it can write directly a PDF. So this is a typical thing what we do. So we write report as a PDF and then we keep it. And if we have to, we will send it to the reviewer. Okay, this is now done. Everything is fine. And then there are different ways, how the validation is done. And then finally, if there is something of wrong, I will show you soon. There is something wrong, it automatically makes a complaint about this. They said, okay, now there is error here. You have two choices. Either you can try to remove the error, that there is something you can do, or if you cannot, you have to explain it. This part here, output validation response form, we can have this there and we can type, for example, okay, the data was bad, our crystal was really badly diffracting. We tell already in there why we get. This is the, so what it does is doing, and then it says this is now done. Here is the report, download GIANxEF report. Click this, it downloads to you. But the point is that there is a warning. It says this report is for guidance only, part of a review of application. Should not replace an experienced referee. So even if you do this, it might be the case that there will be somebody who wants to get really even more deeper in your and see if there's any. Normally that will be enough. That is there. We download that out from there and it looks like this. So I write here GIANxEF, that is one other program, but GIANxEF report. And now it says structure factors mean the data has been checked too. So it's looking, okay, do you have any funny on your data, something missing? there everything is correctly done, and then also looks that. Now that's the same warning as before, and now it starts to print the report. So it says data block is the name, and then gives you how accurate the carbon-carbon bonds are about the wavelength. It gives you unit cell and temperature, and now it's making two things. It calculates theoretically from the information from the zip file. It calculates theoretically what it should be. So it says calculated report. This is the numbers what you have in your zip file, and this is what are the calculated ones. And in this case, the numbers are the same. You can see it goes up here are the same. Now here, and now in here there is only difference. So you can see theta max, and theta min. This means okay, and ref, number of reflections calculated 3044. Have collected 3036. But there is now actually 8 reflections missing. And 8 out of 3000 is nothing. And quite probably this is a technical issue from the instrument. The instrument has not been able to measure these 8 ones. But this is not a big thing. If this is a big difference here, then the program will start give warnings. Now you have not done something correctly, something is or is in. So that is why it is important to do this report. And now run the GIANxEFAML for your structure, included that this is for my students to do this kind of a thing, that once you have done it, you have your tables, then you have the GIANxEFAML, and when you have done your homework, you have to submit it. That's the idea. Then now I'll briefly go, before we go to, I will also show you something about the chemistry database, how we do this. But this is the molecular drawing program called Mercury, also freely available. That was beginning. When you have your file from your structure, you can. There are other programs like Diamond or any other molecular visualizing programs. This Mercury is quite handy. So it works like this. That you go there and open, and then that's the structure. I will visualize this. I will show that it's better for you to. Looks very similar like inside this OLEX, inside the computer, but in here we can start looking at molecular distances or bond distances, angles, or where are the other molecules. All these things, make a packing plots, and that's a very simple thing. So we read here. Now, this is actually how to make an image. So if we want to make an image of the thing and put it in the report, there is a way of doing. So we can save an image, save this screen, what is here. That's the idea. And then it appears like this. Now the image, and now it's in JPEG, you can put it in the Word. But then you can also, inside this Mercury, you can ask it to look for the next molecules or hydrogen bonding. So there is a tick here, H bond, and then when you use it, it will show the atom where it thinks hydrogen bonded. You can see there's a dotted line, but you can see there is an atom here, nitrogen, and there is an O atom here. So why is this? This is only that it looks the distance, it doesn't show them yet. But if you do this, when you click it, you can actually see that there are 2 molecules. There's a molecule here, and that's hydrogen bond. I will demonstrate that also in real life. So it's from OH nitrogen, this thing, OO distance 0.9 is rather long, and the angle is 150. So it's not a very clear hydrogen bond, and that's the end. And then what you can do, I will show it also very easy, make a packing plot. So how the molecules pack. And that's the idea. In this, if you remember, the molecule or the table says how many molecules we have in a unit. And it says 4, and these are 4 molecules. But now if you ask her how many molecules are in an asymmetric unit of this molecule, Because now we have 4 different coordinate sets. We have the original and then those with symmetry. So there are 3 times 2 1-screw axes. But each of them creates 1 coordinate set. It means that there is 1 molecule and then 3 coming from symmetry. So this would be asymmetric unit. Asymmetric unit contains 1 molecule. The rest comes from symmetry. And then, okay. Okay, now I jumped already. Okay, that's what we do later on. Now this mercury version, what I have, because if you take it standalone, it doesn't have the chemistructural database. But you will see what is it later on. But my version has it. So it has here a list of structures, 1.3 million structures. You can visualize each. First, it's one is shown in here. And then there's a top menu. And we can do this, and then toolbar to set any common kind of a setting, display styles, colors, and display area. So these structures, and this is a structure navigator. So in this case, if we are in a database, it contains names of that. It also contains here your structure will one name, other structure. And now here we have this kind of a contacts menu button, which is shows other molecule. I will demonstrate. And in here, we can also exclude hydrogens, all these kinds. This is a little bit that, by doing, learn how it works. And status bar tests can give you some help messages. But it's very intuitive. It's a very easy program to use. But what is there? So the Mercury program leads multiple formats. Most common are the REST file. Remember, this is the results file from your refinement, your rack structure solution, and then you ask the program to write the CIF file. So what is the difference? That is the content, information content is remember, this looks something what you saw already there as an file. There are the coordinates, and now this is now the CIF file. Just information. You don't have to know what is actually inside, but you can see the format side. And Mercury can read also XYZ files and auto files. Quite interesting. But now quite quickly I will go through chemistructural database. And the only difficulty with the chemistructural database that it's not free of charge. So you have to have an national or institute license to use it, but I will show it you anyway because it's a very nice tool of checking if the structure is known. Somebody else did it, and when and where. That you don't repeat the same thing. So you don't publish the same thing. This has been published 10 times already. Okay, I don't want to publish. And referees often, like myself, often check. Somebody says, this is now the first time in the world. I said, I don't believe you. I'll check it from the chemistry. And it's huge. This is an old picture, but now we are somewhere there that is something like 1.3 million, 1.4 million structures. And it contains everything except purely inorganic. So if you have a purely inorganic structure, it's not in a chemistructural database. They say that normally what you have to have is a carbon-hydrogen bond. But carbon is the essence. You have this kind of rhythm. For example, some metal polyoxometalates are there, in many cases. But if it would be purely a hydrogen carbonate, not be there. And then how you sometimes might see it, it's called the ref code. This is that each of the entry, each of the structure have their own individual code. This is what there are. There's organic, metal organic, non-polymeric, single component, multi-component. This number now 1.35 million structures. And I will show you briefly, and I will maybe, if I have time enough, to demonstrate that also. So this is how it works. When you click draw, this kind of a window appears like a chem draw. So we click benzene ring there, and then click also C, and then C, and then click H, so you can see chem draw at hydrogen. So this is the idea. So we do this in sequence. get the benzene ring, then the two carbons, and then I draw their this kind. Now it looks like an ethyl benzene, and this is the minimalistic thinking about ethyl benzene, because here don't say any atoms. It considers that there can be any atom. So now we have benzene ring in the ethyl chain. Now let's see how many we have these. So now benzene ring can have any other substituent. So now we click here, search. When we do it, another window opens, and when we click here, search, this thing happens. So it reads now, and we get 2,406 hits. Each are containing. Now you can see what we were looking for is the red area. But now, because we didn't say that what is here on these cases, it was looking all of them. This is now the ref code here. So this Abadir name for it. So this is the search hit as a ref code. And the number of hits is. And now search, what you have done is defined as red. But now we saw that 2,406 is too much. We can't really get anything out of it, so we have to focus it. So I can go and edit this one here, define a little bit more tile results. Because if your search is really broad, you get millions. Not millions, but hundreds, thousands. But make it more narrow, then we override the existing one, click yes, redo this. So look, we added hydrogens. Now this is really a benzene. Now we do the search again. Click start now. Became interesting. Now it's 52. So only by defining that it's a benzene ring, we kicked out more than 2,350 structures. And now the idea is that now you can see what is ethyl benzene. Ethyl benzene is a solvent being trapped with the structure. This is the real structure. Now you can see the MOF structure continues that direction and that direction there. You can see there are 52 of these cases, ethyl benzene solvent. So with this, we can study the structures and we can look for what is contained. There's something else than our molecule, how it works. Now research goes from 52. Now you want to know who did this. And then you will go there and click the author. You can see here, this is the persons, this is the journal, all the numbers. And there, in many cases, it also knows, click it, you can get the journal directly. This is a very nice tool of looking very similar structure what you have done yours. And then the author and journal details for this. And then this is also there. It's mercury, same mercury, but it's inside the chemistructural database. But it's not so efficient. I was now thinking about the idea that we now, where's the boss? Boss is not there. We could now have some short break, like a 5-minute break now, and then I will show you a bit this mercury program and so on. Before I go to the final examples of the structures, be then more like a scientific lecture, a lot of structures, kind of a thing. Then you can see the products of the experiment. But let's do it now. Let's now have we don't go too far. So have an hour break for 5 minutes. Then we at 1:30. I think we will start now. I will shortly present now the use of mercury, just very simply, because as I said, it's very. This is our structure which we solved, and now you can see the presentation, what we so-called ORTEP presentation here. Now on here we have a many styles. It says ORTEP, and here it says ellipsoid. So you can see we have ellipsoidal presentation, and it's a very nice presentation of of your molecule. But what you have to do often in this case, and this seems to be quite, in a sense, tricky, what happens, quite often the students, when I ask them to do it, they do it like this. Then they send this to me. Then this is my structure. Yes, of course it is your structure, but I can't see anything. So always when you're presenting your structure, rotate it in a position where you have a minimum overlap. So then it's very easy for everybody to see individual atoms like in here. And sometimes you can have a really complicated structure. So it's like I was showing yesterday, the spheres there, the molecular spheres. There's always, because it's a three-dimensional object, whenever you turn it around, there's always something on them. But if you have this kind of a simple molecule, then it's easy to do this. And the point in here is that we can here easily change presentation style. This is the classical ball and stick presentation, where you have all the atoms are presented as balls. But this is, of course, not the real one. The previous one, when you have the ellipsoids, is the real one. But what I always myself always want to show here is so-called space fill, and this is the actual how the molecule really looks like. So it's really the idea that the real shape of your molecule, or if there's a hole or not a hole, can only be seen when you're using a space filling model, the CPK. And now when you rotate this molecule, it looks in essence the same as it was, but it's much thicker, it's bigger. And this is actually the volume what this molecule takes in crystal lattice. But I will show you now very briefly about the hydrogen bonding. I will go back to ellipsoid presentation like this. And now here in the lower part, there is a nice knob which says, look, hydrogen bonds. And now it is looking, but now it's not doing anything more than just looking for what is the nearest acceptor atom. Because here is a donor. Now, this donates hydrogen bond. But now in here, there is no problem. This is an acceptor. But now it thinks that there is now a molecule here, or atom, which could be the donor. But now, if you look carefully, you'll learn it later on, of course, we use here in the right-hand corner now, there's expand contacts. When I go on top, click, it draws the next molecule. If I go here, now it clicks this one. Now, if I rotate this, okay, you can see that there's a chain. The molecules are bound together by this kind of a hydrogen bonded. So now we started seeing how the molecules are talking to each other. And this is, of course, what we have to know in many cases. We are looking, okay, where is the other molecule? How they are organized. And now this organization, if it changes slightly, but the components are the same, then we call it as a polymorph. The different structure from the same molecule, different crystal structure. They might be so that there might be 10 different crystal structures for the same molecule, because they come from the different conditions. Remember, when we grow the crystals, we can change conditions. Now, it might depend on the solvency condition, which kind of structure comes out, even from the same molecule. And pharmaceutical industry is very keen on this, because you can patent new polymorph, even if it's known compound. if somebody has never found this polymorph, you can patent it. That is quite interesting thing, a feature what crystallography has brought. But that's the case. But now I will go back a bit. I will say reset. Reset is a very nice process. It kills everything else. I reach back. But now I will do another thing. I will now ask it to look for one hydrogen bond on. Let's take this one now. And now, if I unclick this one, it doesn't show anything else then. Now it doesn't show the hydrogen bond anymore, but now we know that there's a hydrogen bond. But now there is another trick, because in real life, there is no, these doesn't exist. Of course, this is just a presentation. Like in here, there's no such a bond here. This is only embedded, it's right there. So this is just presentation. So if in order to see this nicely, is to use the space filling for this. We do this. I click space filling. Now you see interesting. Now I will change it back. Have a better orientation. Trying to like this. Now look this region. So there is the hydrogen bond is here. But it seems to be that the atoms are like floating very far away. But that's not the case, because when you click here, space fill, you see now that this hydrogen now interacting, hydrogen bonding to this one. When you're using the space filling, you can really see the bond. Not just a number, you can see it visually. This is how it goes. So now let's reset. Thing, go back, ellipsoid. Now what we can do easily, of course, now I will show you quickly. Let's say measure distance here. And now this is the same number which was there in the table, but sometimes it's better to show some features in the picture. So you can do it and keep it in there, and then you can take a print out of this. Okay? And are just clear measurements. Now, the point in there that if I would like to see more what happens, so the other form is this. I can look for the interactions, but if I want to see the whole thing, where are the other atoms? That's the packing. And then the packing is actually, there is a knob here in the left-hand side. Packing, this. And now, this is a typical mistake. In many of the forums, you say that, okay, this is now a view along certain axes. So A axis or B axis. But if you now look carefully, it's not. This is not along any axis, because it's like a sideways. So when you do this, you have to be careful, have you said, but in here there's a knob, there's A. Now the view is along A axis. So we are looking, here is the origin and A, we are looking from this direction. So when we are looking along A, we have a BC plane. So that would be the view of packing along A axis. And then you ask, okay, what is the same thing along the B axis? Just go here and click this one, and that is the view along B axis. So the packing is different. And then, of course, you can look that also from the C axis, and then it looks like this. This is the worst view, because there you can see the other molecules are in front of the other ones. So it seems to be, in this case, I think so. That went back, but it's now it's on, but doesn't. Maybe it's a battery. I will keep it as long. Could be battery running out from. No, that's the idea. So that would be the nice view, but this is not very pleasing because now it's looking upwards. So what we can do, there is additional thing in here. We can go, okay, say rotate set 90 degrees. And now we have a nice view. So we have an origin here and along a-axis. We have an AC plane where it's looking, and that's the idea. That would be a very nice view of packing. But now this is also the idea when this is the normal way of showing this. But this is not true. Because immediately you would ask, what is there? What is there on this side? There is a lot of empty space here. So can it be so that the atoms are floating? That is not actually true, and that's why it's always better to look these things, what you have, really on a space filling. Now you can see there is no empty space. So it's completely full. And to show it even better, that will be the last one we will move. I will go here, ask it a packing. Now I will ask it to calculate a bigger area. Now this is 4 unit cells. Now when I rotate this, now you can see that there is absolutely no empty space. So this is so-called closed packed structure. So all the molecules are packed like this. And now we have been talking about the COFs and MOFs and all these porous materials. It means that then in the structure there will be a pore or a cavity or whatever. But in this structure there's not. So all the molecules packed this way. And this is what we can do with this program. We don't have time to go through and have a rehearsal or practice this, but just download, get the program. You have the file, then you can play around with this, or with your own. Maybe now or in the future, if you're doing this kind of work, you can use it for that purpose. But now, let's now move to the final thing. Which might be scientifically more interesting, because these are the examples of the structure that they are showing example how kind of systems have you single crystal. Remember, everything comes from have to have crystal. Get the crystal right channel. Paper, ever large complex. Just to remind you, have to have the order. Has to be nice crystal. The actual idea out from there. Practice it. Study every behavior. Ever an actions. Quite also, I did in more complex. Actually, how so this work is my first primary. Bicycle. Helicase. Double. Okay, that the that it's cyclic structure, so it's a long one. So it starts from here, goes up there, and then on the other side it starts from here. This is how it looks. And now there's an anion in self-formed helical cyclic structure by self-assembly. Also quite old stuff. And the point, this is S2001, and one of the paper was Canadian science Canadian. Then I did also some other catenane work. Had an interesting thing. So there's a catenane. The catenane is two microcycles joined together with mechanical bond, like a magician. And now here we have an X-ray structure, a very catenane. Always show it like this because you think, okay, there's a lot of empty space here. No, this. But now you start seeing there's a pi-pi interaction. Pi is the, but the most interesting, there's a laser group, molecular break. With light, you can change this. This conformation, then that was also quite old. Actually, just before. Yeah, okay, that's fine. That we'll go back. Catenanes. And remember, the instrumentation, what we had 25 years ago, is nothing what we have now. So these were rather complex things to be done. But the reason here why these were successful was the crystals. We got big enough, good enough crystals that we can have this. And this is not considered a very complicated structure. One of the simple. But anyway, the catenanes is a very nice family of compounds. Then what we did also have done work rotaxanes. Rotaxane is a system where you have a microcycle and then you have an axle here. So there are 3 microcycles like this, and then there's the rod going through. That's a rotaxane. Again, this thing comes by itself. So you mix the components, the solvent, and wait, and then you will have this. So that is a rotaxane. And you can see here, this always gives you slightly different opinion about this of you, but that is how it really looks. So it's really compact structure. So nature normally, especially in a solid state, doesn't like vacuum or empty space. So molecules normally have to touch themselves. That's what happens here. There's pi-pi interactions with. So we did quite a lot of work with Jean-Marie on his rotaxanes, but we also then later on, in 2007 or so, in early 2000, he was interested in grids, the molecular grids. The molecular grid is like a MOF, but actually it doesn't make a framework, so it's make a discrete molecule or complex. So the idea is like a grid. So there's 1, 2, 3, 4 atoms here, 4 ligands, 2 in this direction, 2 in that direction, you can see here. In this particular case, there are 2 different metals. So then you can do photochemistry or whatever, you can study how this changes. That was a really quite hot topic subject 20 years ago. And then we go to bigger systems. Now you can see molecular weight is 6,500. And this is now the construction. So you can, there's a porphyrin with the 4 pyridine rings in here. And then this kind of a curved system where you have a porphyrin, zinc porphyrin in there. This work was done by Jean-Pierre Savage, who got the Nobel Prize some years ago on the discovery of molecular machine. This is not the molecular machine, but this is a very nice example about that we can scale up. This work was done 2009, so nearly 20. And this is how it looks like. It's very bad looking, but that is actually how it really looks. So here there is a tiny hole, this area. So here it's huge, but now you can see here that it's a tiny one. That's the case. So now we can have structure, atomic resolution. But then the idea is that he sent me this. So it's a very impressive molecule. So it has 524 carbons, 52 nitrogens, 30 O atoms, 12 phosphorus, 24 fluorines, copper, and zinc. The molecular weight is about 9,000. When you see this kind of a molecule, which has a long rod, you can see that, look how lipophilic this part here is. That also has this kind of a thing, a huge structure like this that no way you can do. But I would, of course, not show it to you. That was not done. So actually, we were able to do this with our in-house instrument. And now this is the X-ray structure of that. Here are the ideas you can see. It's curved a bit in this direction. So in here too, and the zincs are there. And we could even see that there is a molecule attached to water molecule. So we get more information from done. But that was really the idea. And why Jean-Pierre Savage was doing this, he was doing molecular press. So the actual idea is that these parts here are able to move around these. So they could trap molecules inside here. This is an empty one, but that's the case. This is how it looks with the K. These are the 4 anions. So it's a really huge structure. And this was published in 2008, and then 9 and 10 were the papers on this kind of a rotaxanes thing to do. But now let's go to a little bit more, because I was showing you the structures before. Get this kind of, because they were molecules. But now I will show you a couple of examples that when you do this thing, you quite probably don't know what you get. And then the analysis of what you get, very difficult, and you have to be very convincing. So let's make a tetrahedron. But let's make a tetrahedron that is not existing. So we take all the components needed for this, And the idea is that then we call this metal ion assisted self-assembly in water. And now this thing has 22 components. 22 separate things are put in water simultaneously. So what happens? You would easily consider that you would have a big mixture, get the polymers and all this kind of not clear stuff, but no. Really, it works like a clock. This is what happens. And now, we take the spheres. These are the metal cations, what we there. Then we have two different types of ligands, organic ligands. We have the green and the blue one. They are separate ligands. Now we put all of them simultaneously in water. Now, what happens? There will be metal ion assisted self-assembly, and even so that you can consider that these are subcomponents. So we don't have the ligand yet, but it will be formed by itself from these components. And self-assembly creates this. So now you can see that we need two of the green ones and one of the blue ones to make a one edge, and then we have the metals in the corners. That's the tetrahedron. It happens in water by itself, quantitatively. So X-ray structure. Now, why this was interesting is this. So this is now an image of not a metal, although it looks like a metal. This is white phosphorus, and the white phosphorus is kept in water or underwater, because if you take it out, this happens. It starts to burn. So you have to keep white phosphorus water that it doesn't burn. So it's the idea of what happens here. The white phosphorus is P4, spontaneously ignites when it's out of water. It's dry, it burns. And now you ask me why. I will show you this. Remember what we did, or the nature did by itself. It made a tetrahedron. And now, what is the structure of a P4? Not linear. Start thinking about this thing. It's tetrahedron, but it's a small one. So now, let's do this. So we did it. So when we did this and we put all these things simultaneously in the water which contains white phosphorus goes inside the. And now it's trapped inside there. We call it white phosphorus and is encapsulated in one. And you can see here what are the ligands. A very simple ones. The pyridyl aldehyde and then this diamine with this kind of a sulfonate groups in the P4. Now in the water, if you have water, you put there benzene. The benzene will kick out the white phosphorus, and that benzene goes in. So we can exchange. Of course, you will ask, why is this possible? Okay, here we have it in cartoon. So we have a pink solution of water where the white phosphorus is inside a cage. We put N-heptane, nothing happens. Because now the N-heptane cannot go into cavity. It's like a bear, and this is a snake, so it doesn't want to go there. But now benzene is like another bear, a bigger one, which kicks out the white phosphorus. Now the white phosphorus comes out from the cage, and now the cage contains benzene, and that's there. This is actually what we did. This is now the X-ray structure. The X-ray structure is really crucial of showing that the white phosphorus is inside. So it's here. Now you can see the rotating image. So it was rotating a bit. The idea that here is right, and then here we have the white phosphorus, and I draw it with the space filling model that you can see that it's really tightly. Now remember that if you take white phosphorus by itself from water, it burns. This doesn't. So we had it in the table for 3 months, nothing happened. Because you can consider that it's like a fire, put it inside a bottle. So it doesn't do anything as long as in there. Immediately when you open it, it burns. And this happens also. If you take this and you grind it, that you break the cage, it burns. And that was the science paper And there is a colleague, President Mal, who is now in. So we did the same thing. So what we did the similar things. We had an idea that we can encapsulate white phosphorus, which is like a 4-atom tetrahedron. Can we encapsulate an atom, single atom, right there? And we worked with the physics group in Finland, who are very famous on hyperpolarized xenon. What we did in this, we trapped xenon inside the cage. Again, the same. These are the components, very simple, iron, and then in xenon gas was there, and this happened. We didn't have the X-ray structure of that. Unfortunately, we would have a very nice NMR. We can see in NMR, okay, yes, here we have cages where the xenon is encapsulated. It happens by itself. So we continued the work ourselves. These are the similar cages, but now with the different guests in here, the point in there, and then we got a lot of X-ray structures. They're all different. So inside there, in each of them, have a different guest. And now this is how it looks like from outside. So there is a chloroform, dichloromethane, tetrachloromethane, so on, tetrabromomethane. We published this something like 10 years ago. And then there was a collaboration also with President Mal, also in this. Now, can we make something different? Can we get an X-ray structure of it? Okay, now we made their tetrahedron. Let's now make a cube. A cube needs 38 components. And now we are approaching the molecular weight of 10,000. As a single molecule, isolatable molecule, we have to make it and crystallize and then get the structure. This is the synthesis. It's a very simple synthesis because you can buy the compound. You can buy this. This is commercially available, and also the pyridyl aldehyde. You mix them up only with the iron 2 triflate in EMF. That's the intermediate, and that's the thing what happens. And now, X-ray structure is very important. So that is it really a cube with no windows? And there is the X-ray structure. So this is now one view. This is another view, and here we can see the CPK, or the if you can see all the space filling model. There is no windows. It's really a cube, really a box. But it's not, because it consists of metal cations in here in the corners. It is a complex which can open and close. A little bit like what we had the idea, how can the tetrahedron trap other small molecules? It has to open. So we did the study, or Nietzsche did the study with this, with hydrocarbon. Here you can see the X-ray structure of it. It's an empty inside. So if you take coronines, 3 coronines will go in. And then if you take your C70 and put the C70, the coronine will, these coronines in here, will kick out their C70, and then you get here. But if you have an empty case like this, when you put C70 there, it's C60 there, it goes there. But now if you put C70, also goes in there. But now in here, in this case, if you do C70 in there, it kicks out C60. So it means that C60 is less happy inside the box. And if you put C70, C70 kicks it out. So it's like a football in a box with bouncings around. And C70 is a bigger. And unfortunately, we never get an X-ray structure of those, but that was shown by NMR mass spectrometry. But that was the X-ray structure of this one. And it was also done a little bit more than 10 years ago. And now, can we do an even complicated thing? That's the reason. Hopefully my trousers will stay, hopefully. I need this for that. So the point in there is that can we make a knot on a molecule? And then how this is possible, because you know that it's very difficult to control a molecule in solution because it has a Brownian motion and it has all the possible conformations. So how in the heck can you make a knot? And even better, can you make a 5-fold knot? that it goes pi times. So let's try this. And it's interesting, it only has 15 components. It's about 5,000 the molecular weight, so it's rather large, but let's see how it goes. So we take a rod. They're all the same rod, but I keep different colors. You can understand what happens. Now I have then 5 other rods, which are the same. And then I need this type's 5 balls. These are, of course, you can imagine, metal cations. So let's mix them as previously. Let's see what happens. Nothing. Nothing happened. So we realized these were incorrect ones. We have to change now the spheres, the metal cations to different one. So we change them, and this comes out by itself. What is this? Now, you can see the colors are here, same colors, and then these are the connectors in the corners. Then there is something strange here in the middle. These violet balls seems. What is this? This is a pentafoil knot formed by itself. It's in the Moroccan flag, but you can also do it at home. This is the easiest way to do it. It's the same thing. Now, the actual idea or the chemistry is very simple, or not. So you have to synthesize this, and then you have to take the connector point, which is this kind of a ethylene glycol-based diamine. Then you again have iron in there, and then later on you do an anion exchange, get it crystalline. And this is actually the molecule, the knot. This is how it goes. It will be very complicated to see, but I will show you better that it is really a knot. So it's the idea is there that the molecules goes like that. So that's how the X-ray structure looks like this. So you can see there is no empty space. So it's really a tight knot. And then in here is now these are the same connections, but I deleted all the atoms which are not part of the chain. So let's start from here. So we are on the top, go here in the loop, and then here it goes down. Then in here we go up, loop, down, up, loop, down, up, loop, down, up, loop, down, and again. 15 nanometers long thing, which does this by itself. And the point in there is that this is how it looks. This is the X-ray structure of that. And then the idea, we actually sent this to science, but they said, no, it's not interesting. And then we immediately sent it to Nature Chemistry, and it was accepted in 120 minutes. So in 2 hours. Nearly instantly there. And then they wanted us to draw. They said that, okay, this is so nice that you can get the cover, Nature Chemistry. So we prepared a very nice looking picture of this kind of a thing, and that's the chloride here inside there. And the idea is that they were not happy about this, but why this is so interesting, we'll show you the idea is that what really happens. So this is now the 150 atoms, 50 nanometer long thing. And then when I start doing this, you can see what happens. So then I will close it. This. And now, this is our, okay, it's not that nice looking, but here we have our pentafoil knot. So you can see it was that long, and the squeeze it's like this. It's impossible to do it in any other main like this. So you assemble it, you build up that, and then you connect the corners. So we were very happy. Actually, I did one form, and they did also this kind of, but no, the journal said no, not good. So they made their own one. And this is now the cover of the Nature Chemistry. Here we have our knot is there, and then the chlorine is there, and then it says here, star is born. This looks like a star. And after that, they bleed it, Star David, and all these. Now, a little bit more, what we can do. So sometimes you face a really big surprises. This is a very interesting thing to show you what happens when the X-ray structure can tell you. So I got this kind of a structure, the microcyclic, relatively small amino acid-based microcycle. And this is the person. This is Stefan Kubik from Kaiserslautern, Germany. And then this thing was there. You can see what is there. This the phosphate, pyrophosphate, the diphosphate in there, crystallized from acetone. And look here, the mass of this compound, including everything. So these are four, because this is cations here, and this is the idea. This is neutral. So we have a salt in. So it's a trigonal or ternary system. So the molecular weight of this should be 1,702 roughly. But now what happened? So we found very nice, well-diffracting crystals, colorless plate, very good. Of this size, rather small, but this was decent, okay, and it gave a unit cell. Remember, we have to get the unit cell in order to get the structure solved. And now the A is 22, B is 31, C is 61, and the angles are 70, 80, 70 something, so it's triclinic with a volume of 40,000. This is typically an indication there is something wrong in a crystal. So it's not a single crystal, it's something else. That whatever is coming out from there is not true. But anyway, I decided, okay, let's try this and let's see what happens with this. And the idea is, why is this? Because if you calculate, remember, this is the formula, what we saw earlier. So density equals the number of the units with the molecular weight divided by the Avogadro's number in Ohmströms and volume. Density, number of formula units, and so on. Now we calculate. So we estimate that the density of this is 1.2, like an organic compound. This is now the Avogadro number. This is now the volume divided by 2, because in the triclinic system we should have 2 molecules in there. And it says the molecular weight of the thing should be 14,000. How is this possible? How can it be? Because we have this, which would be 1,700. How can it be 14,000? Something must be wrong. But the point in there is, now, turned out to be that it was a very good crystal. I could solve the structure, and these are all the atoms which are there. So it was not one single molecule there. It was a big group of things. So what is this? This is actually a constitution of this type with a molecular weight of nearly 13,000. So our calculation was correct. So the molecular weight there in the asymmetric unit, so what we have to define is this 14,000 roughly. And what it actually is, it is a combination of 2 of the microcycles, 2 of the cations trapping 2 phosphates inside there. And then there are several of these. So it was really a complex structure, but we didn't have no clue about this, what it is. So here are the different presentations. The cations or the anions inside are blue, cation is green, and then the microcycle is red. And you can see very compact. It's really like this kind of package. And it has 2 components. And then there are more of these in there. So this is a different presentation showing now the anion species inside the idea. The cation is there. And this is so-called Hirschfeld surface, which tells you that there is a really strong interaction of the anionic species with the microcycle. So it traps it, but it cannot trap it 1-to-1. It traps it 2-to-2 fashion. And then the cations are blocking there. So in the lattice there were 4 of these capsular entities. TPA cations and then the phosphate anions. There are, because even with that data quality, we couldn't locate 5 TPAs, 9 acetyl-aldol products, because now there were also acetone dimerized in there. We saw that, and 1 acetone and 1 water. So we see 13 TPAs because there should be 16. So this, even the structure was lacking atoms. But we couldn't find them. They were somewhere there floating, so badly visible we located. But we saw all the important things. And then the idea, it was published in Chemical Science about 7 years. Then what you can do with this, you can look interactions. One we discussed already yesterday is anion-pi interaction, and in the solid state. So anion-pi interaction is pretty kind of controversial a bit. And then the idea is a possible on competing interactions with anion. So ion pairing, you know, because when we have anion, there has to be cation. Now, and we have a coordination, it can be so that the anion coordinates to metal. We can have dipole anion interactions, of course, because if we have anion here and we have a dipole here, it's a positive charge of interaction. Or we can have a hydrogen bonding, of course. This is very well known that the hydrogen bonds to the ion. Or we can have halogen bonding. This is what I discussed yesterday. And now, finally, what we have here, this is what we look into. This is the anion-pi interaction. So we have a pi system, and we want to see if the anion interacting with it. So there was a Ben Hay already done something like a little bit more than nearly 20 years ago, did the computational work on this kind of a thing, Alzheimer or the other compounds, and which proposing, okay, this kind of a species exists. So our idea was to try to see if we can get an experimental proof for this by X-ray diffraction. And the point is, I got a student coming from a 3-month internship in my group from Germany, and we had an idea that, okay, let's study this simple salt. So we have here a highly polarized pi system, and here we have the cation, and anion is here. So here we have a chloride, here we have bromine and iodide, and here we have the same chloride and bromide. And then, of course, you can have a phosphonium in here. And it was a big surprise for us that actually worked. And we got a lot of X-ray structures of those showing these. There's hydrogen bonding, of course, but now they started also anion-pi interactions here in this direction. There's a strong hydrogen bonds in there. Here you can see it's really there's both hydrogen bonding and here anion-pi interactions, and the same in here. We started a project with Markus Albrecht is his name. We do this, and this was after 3 months' work. It was published. So the student Claudia Vessel got a really nice paper out of 3 months' work. And then that was the idea. We saw like this one here that you can see that anion can sit also on top of 2. So what we did, you can't see all of them, but then we took a PhD student, a German PhD student, do the work, has he synthesized all these things. And we published this pile of papers on these. All in all, there were more than 110 X-ray structures. Of course, you can't see all of them. In various levels, looking for this kind of a thing, we found out this analysis of which kind of things we can see. So we can see eta 1 where it's around 1 carbon, a 2 or 3, 4 or 5 or 6. And surprisingly, the most abundant is the 3 type of thing in solid state, and then becomes each. This must not be disturbed system. This is a very typical thing, what is there. What we did, we actually wrote 3 big papers out of it. 1 chemical science, 1 chemical reviews, and 1 ChemCom, where we published all the others between 15 and 16, and coined this kind of let's say, graph out of it. But the point, because we have the receptor, and then there can be additional interactions. And then there can be lone pair dipole interaction, hydrogen bond, cation-pi dipole, hydrogen bonds can be with a cation. Okay, cations have a cationic repulsion, they don't like each other, but if there's an anion, we can have anion interactions and so on. So the idea and solvents play a big role in here, and then anions have electrostatic. So all in all, coined kind of a thing, we're able to show that really anion-pi interaction exists in solid state. It's weak. You have to define the limits. What is the anion-pi interaction? But this is a very good example of using single crystal X-ray diffraction extract information, data from the structures. You can't do it from one structure. You need 100 structures in order to the really trend. Nobody will believe if I say one structure, it's there. I said, no, I don't believe. Show me more examples. So we showed that there was a 100. And if I remember correctly, that was the last one for the examples. For these, we are nicely still on time, 3 minutes. And that was the end of my part. Then in the afternoon, we will have the innovation workshop. I will be there also. Now, you have a chance to ask questions now, or you can then ask them after there and during the innovation. Go until something like up to 5 or so. Then we will. But if you now have any questions, we have free to ask. Yes. Yes.
I
Yes.
did not get.
Yeah.
So my first question: compound is leak,
Yeah.
and I want to check that.
Yes.
So
Yes. Yeah. There are many ways of doing this. Depends on how liquid your crystal is, how large it is, what is the properties of this. The first thing I would look at, okay, can you protonate this? If you can protonate this by acid, I would do it and I would make a salt. Then try to crystallize if it doesn't break down. So if it's kind of everything stable. And then the question is that is it liquid in the normal room temperature? Does it solidify if you go down in the temperature? What happens? That's one thing. And then there is the ultimate thing in there that if it's not too big, cannot modulate the molecule at any way, then there are two possible ways of doing this. Both are rather complex, but the other one is relatively simple. So you take a solid major, you take a molecule with, you know, that crystallizes. And then you make a mixture of your liquid and then in this solid and try to crystallize them together. But actually the more solidifying component would like take your compound like a solvent molecule is coming to the crystal lattice. And if you can do that, then you can get the structure of your liquid thing. Or then you can use Makoto Fujita's crystalline sponge method to recreate a moth. And in the moth, there is big enough holes that your molecule, the liquid, can go in. And then you just take the crystal, because its crystal is stable in that solution, and you soak the crystal in a solution where a target molecule, the liquid, is, and then just take the crystal out, and in nice cases, have your molecule, their liquid side, your metal organic framework, and then you can get the structure of it. Because you can have the extra structure as an empty one or some other solvent and mirror with your molecule. So these are the ways. It can be done, but it needs really a lot of information, chemical information about the nature of your molecule. But the protonation is, or if you can do any other modification, chemical modifications. So for example, it's an acid, make an ester out of it. All these kind of things without destroying the actual thing, because you're looking for the core of what is the structure of the core. Then whatever attachments you would help you. For example, carbamides are able to make a carbamate. Carbamates are often very nicely crystallized. So there is these direct methods and indirect methods. But that is, I could give you maybe a better advice if I would see your molecule. I said, okay, try this, and that it can be done. So if your molecule is liquid, I would not give up. I would think, try to figure out the system. Yes.
worst case chemistry,
Yeah.
we can test
Yes.
from host on pH of
Yeah.
what type of host molecule design that can release the gas according to pH.
Okay. Quite probably it would be some in or something like that, which is sensitive to, because it means that the microcycle itself has to be sensitive. It's not the guest, the host, which has to be able to open in a higher pH. So probably that would be something which would, let's say that in the native state it will encapsulate your guest molecule, but when in water, cyclodextrines are something like this. They are soluble water, soluble and they can trap something. But then the idea that you should, I think, modulate the cyclodextrin so that you will have some groups in there, and whatever, which would be then being protonated depending on the temperature. Let's say you want to go down in it. So you add acid protonates the amino groups, then you will have some kind of additional push out the guest from there. But then also it could also be happening, I would study that first, not just a plain neutral microcycle, which is water soluble, and your guest, the host mass complex, and then just going down in pH, because the pH itself changes the behavior. It might be so that it's happy inside in some pH, and then in the lower pH or so, it wants to come out. But it has to be tested. So there are many ways of doing that, but this is the simplest way to do it. Just everything in water, have a water-soluble host-guest complex, and then just adjust the pH both directions. But of course, if you want to go the more the acidic side, titrate and see if it still stays there. This will be easily done in NMR. If you do an NMR, so the guest is inside, then when you start adding acid, you see if it comes out or not. That's the case. Okay, welcome. Good question. There. Yes. 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 Very good question. Yes. So the idea is that the fundamental thing is that you need extremely polarized pi system. It's done with the fluorine atoms. But the fluorine atoms will make the carbon atoms electrophilic. So they have, you can consider like a little bit like a positive charge type of a thing. And then the anion has a negative charge. So that's the idea. So the electron cloud in this let's say pentafluorobenzene, electron deficient, and then you have an anion which is electron rich. That's the idea. That's the driving force. Yes, yes, absolutely. With the benzene, it doesn't work. You need very strongly pulling electrons that is because carbon doesn't want to be nucleophilic. So you really know pi system. You really need a strong pull. And in this case, we studied, but it went very fast. We had many different types of fluorine atoms. We had 1 fluorine, 2 fluorines, 3 fluorines, 4 fluorines, and so on. But the strongest is, of course, 6 pentafluorine, hexafluorobenzene. But then you can't make anything out of it because the molecule itself. A lot of this. Yes, yeah, this is the idea. It's a Coulombic or whatever, like a little bit like electrostatic or charge transfer type of interaction. But it's weak. It's quite weak. In solution, normally you don't see it. So they will be because an ion pair, in a solution, it will open. It is so weak. Cation pi is much stronger. Okay? Yes. 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 Yes.
Similarly, as
Yes.
at that as
Yes. It is. You can do it, but the point is that it requires a precious cell. So it needs a certain idea because the point is that you have to keep, if you push gas inside, let's say a moth, you have to keep it there, because if you take it out, you push it in the high pressure, and you take out the crystal, the gas will go out. But if you do it, there is this kind of a device called gas chambers, where you actually you can put the crystal in there, you can pressurize that with the gas, single crystal, then you pressurize this, and then you put some like, I think 80 bars or so pressure, and then you do an X-ray on it. So that has been done for carbon dioxide by my colleague, and it's done. It's a relatively simple technique, and it can be done with the normal diffractometer. So it is possible, but it needs that if you want to have a gas inside or this kind of a thing. The difficulty is really that you need a high pressure for this. Then you have to protect. It has to be on the same pressure all the time, because otherwise it will. But it's possible. Yes, of course. Like what we were doing, we put the xenon inside a cage. We actually never managed to crystallize this, but it can be done. It doesn't matter what it is. So the only thing is that you can get it organized inside there. They have to be ordered, and then they have to stay there the whole measurement. But it doesn't count what is the gas. It can be neon, krypton, xenon, whatever. It can be a noble gas, any kind of a gas. But the point in there is that based on X-ray diffraction, it has to be ordered. So the gas has always to be sit in the same position. And then you see. That's the complication, but it can be done. You get the point? It doesn't diffract if there is no order. This is what I was teaching you in the beginning. So also the gas has to be ordered. So all the atoms in this crystal have to be ordered, because if there is an ordered structure, let's consider MOF, then you have any molecule of gas which is not ordered, then you don't see it. Because diffraction happens only when there is order. And that's the idea. So that's the tricky. That's why the crystalline response method is a very genius invention, that it tries to organize the coming test grid always in the same place, in the same orientation. Even that is another trivial technique. Gases are even more difficult. Consider that you have a monoatomic gas. There has to be a pocket inside a crystal, a cavity where it goes. If that's the case, that's there. It can be. In principle, and theoretically speaking, it can be done. It needs the order. Yeah, klar. Yes, that is real. Yeah. Okay, a very good question again. Because the point is, by nature, all the atoms, or in this, I showed the demo structure what we had, it was closed packed. And then the idea is there that the molecules can be very close to each other. They can really be like this without no interaction. Because the point in there, then we call so-called packing forces. So the actual it's like a big pressure from all the other molecules will force it to be in there, even without interactions. So if it's something which is completely unknown, let's like that, this, you can do computational, quantum computational calculations if there is really any interaction, real interaction between things, or if they're not of this. So you're absolutely correct in that sense. That only the closeness of the atoms in the solid state doesn't mean that they're. So in our case, we always try to show this also in solution. Like I showed yesterday, that we can see, we can run on NMR, okay, we have these components in there, so then it's the real interaction. Then you just crystallize it. But it can be also so that in solution, you don't see any interaction, but you see that in solid state. Argentophilic, so silver-silver interactions are a very good example of it. They are very difficult to see in solution in the normal means, but in solid state, you see there, it's really kind of a thing. So you have to do additional studies confirm that it's a real interaction, not just packing. Because you can always say, okay, this comes from packing. You have to be very careful. This is very good. Yes. 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 But we see this whole assembly also in solution by NMR and by mass spec. So there is additional information. So I told you in many cases, X-ray diffraction itself is not a proof what happens in solution. Because it might be the idea, as you pointed out, that okay, it's completely scrambled solution. It only forms when it's in solid state. But no, this forms first and then crystallizes. There is a proof. NMR and all the others. We show that that's. There is. I will show very briefly the phosphorus NMR. And we already, because it has to be inside, because the phosphorus peak in the solution is different. So that's the idea. Yeah. Doesn't break down. Yeah. The point, and normally it happens so that because the point, this happens from water. So in this X-ray structure, there is a lot of water in the crystal structure, which is not shown. So of course we don't show there is cations. This is anionic. There's a lot of cations and water. It is like surrounded with water. So the actual idea, it's the X-ray structure. It's not only the tetrahedron. There are many other things it keeps in. So it's like surrounded by a water bubble, and then these are hydrogen bonded to the next one. So we are sure that nothing happens to it. It's like contained. Yeah, it comes by itself. There is no technique. It just takes it. We can't know it beforehand. We know only when we have the structure how much water is there. We can't say water go in. Can't do this. Just do it and then see afterwards. That's the idea. No control.
Afternoon, sir. I am having
Yeah.
you showed the catenons.
Yes.
The catenons having a interlocked.
Yes. Yes.
They are interlocked
Yes.
macromolecules.
Yes. Yes.
So, what makes them interlocked, and how the ordered is maintained by the other catenons?
So this is a very good question. So the point, in order to make the catenane, you have two things. So first, there has to be a cycle. Normally that is there. So two components forms a cycle. But then there is a third component, the same component, which goes like halfway of this, and it goes like that. And then the fourth part comes from there. So it's like you take four halves, you can do it yourself. Make first a cycle and then put the third component through it and then clock it from that side. This is how it works. But what it means that the components have to interact. So this thing has to interact so that the other component can be like this. So there is interaction. It's pi-pi, metal coordination, any other, like in this case, what I was showing, there's a pi-pi interaction. So two things went close by to each other by this. So there has to be a force interaction between this component. And then when the interaction is there, then the closing happens. That's how it works.
Have to take the long chains. Have to that by some interaction.
The long chains are really bad because the long chains are, if you speak about the alkyl long chain, this is really very difficult thing because there is no functionalities. So let's say the force of how the long chains will interact with each other is very weak. We need stronger forces. So this is really like hydrogen bonding. Metal coordination is one which is started the whole thing. So you make this kind of a cross complex and then you just close it. And some of these things, like there is the knot or the others, forms by themselves. You don't have to think about these things. Just mix up the components, but there has to be interactions.
Okay, sir. Thank you.
Yeah.
Sir.
Okay. One more. Yes.
Question,
Final
sir.
question. Yes.
Mention
Yes.
need to have atom
Yes.
which allows it to open up.
Yes.
Right. Situation.
Yes.
What do we need to like?
That is also a very good question. We never saw halogen bond, the I plus capsules open, because they form 3 center 4 electron bond. So it's like a one bond, not the coordinated bond what we have. Let's say we have a tetrahedral metal cation and there are 4 ligands. One of the ligands can take off and return back. But in our case, if that happens, it breaks down the whole thing. We never saw this in the I plus system because it has quite a lot of covalent typed nature in there. So it's not as reversible as the normal metal coordination. And that's why we can't do it reversed. Because there's a question, can you reverse it? But we can't. So it's when we get it, it's there. Then it just breaks down by itself. But we can't do the.
Not to like capsule.
Yes, we can, but it has to go. Yes, we can, but it has to go from the window. So that's the idea. Because in these, the box what I showed you can encapsulate CCP, but it has to open. But because now the silver one or the iodine one capsules can't open, there has to be a window. So it goes from the window. We have had some studies for this, but it's very complicated to see them in. That's the idea. Okay, thank you. That was the final. Our chair said that was the final question, so I think now we are happy with this. And it means that all the lecturing is now done. We will now have a break until 2 o'clock and then go on with the